Welcome to episode 5 of this series on differential geometry. In this section we talk about one-forms. A one-form, phi, on R3 is a real-valued function on the set of all tangent vectors to R3, such that phi is linear at each point. That is, given a point a times v plus b times w, phi of that point is equal to the linear combination of the application of phi on those vectors. So a and b represent real numbers, v and w represent points of R3, which are applied to the same point in R3. And then we simply obtain the linearity condition written down there. If f is a differentiable real-valued function on R3, the differential df is the one form such that df of the tangent vector vp is equal to the directional derivative of f in the direction of vp. Let's just check that the differential is indeed a one form. We know that the differential is a function on tangent vectors. By theorem 3.3, we know that the directional derivative is linear in its arguments at each point p for any vector v. To be clear, theorem 3.3 is about directional derivatives, and since the differential is equal to a directional derivative at each point, if the directional derivative is linear, then the differential is linear. This is why we can say that the differential is indeed a one form. Now we claim if phi is a one form on R3, then phi is equal to the sum of fi times dxi, where fi is equal to the image of the natural basis frame functions ui under phi. So these functions, f1, f2, and f3, are called the Euclidean coordinate functions of phi. In order to prove this, we check that both phi and the sum of the fi dxi's will give the same output at each point, at each tangent vector vp. First, we check that phi of vp is equal to phi of the sum of the different components of vp, which are written in the natural frame field. We use the linearity of phi so that the vi's can be brought out of the sum, outside of phi, and then we just consider phi of the ui's at p. Since we've defined phi of ui to be equal to fi, we can replace it as such so that our sum becomes the sums of vi fi of p. This is all by our definition of phi. Then we also check that the sum of fi dxi applied to the tangent vector v of p is just the sum of fi of p vi. That's using the definition of the one form dxi. Since both of these one forms give us the same value at each tangent vector vp, these one forms are in fact equal. Now our first corollary is that if f is a differentiable function on R3, then the differential df is equal to the sum of the partial derivatives of f in each of the xi times the one form dxi. We check that this formula is true by checking that both one forms are equal at each vector, tangent vector VP. Now we obtain a product rule for differentials. Let fg be the product of differentiable functions f and g on R3. Then the differential d of f times g is equal to g df plus f dg. We obtain this product rule for differentials by tying it back to directional derivatives. So using the definition of df, we have df of the vector tangent vector vp is equal to the directional derivative of f in the direction of the vector vp. Then we rewrite the differential of f times g applied to the tangent vector vp as a directional derivative. Then we use the product rule for directional derivatives, and then again use the definition of the differential to rewrite this in terms of differentials. Finally, we have the following lemma, which is our chain rule for differentials. Let f be a function on R3 and h be a function from R to R, and suppose that these are both differentiable. Then the composite function h of f is another function from R3 to R and is also differentiable. Then the differential of h of f is h prime of f df. We use the ordinary chain rule to obtain the coordinates of d of h of f. So partial h of f partial xi is h prime of f partial xi. That's just the ordinary chain rule. Then we obtain, by our earlier formula, the differential of h of f by writing it as a sum of the derivatives of components. Then we replace this partial derivative of h of f, and then we factor out the h prime of f, which is common to each of these summons, and then we use again the definition of the differential of f and obtain our formula.